Practice exam 3, part 2. We're up to question 6. So I already talked quite a bit about doing CQN equivalences. So question 6 is just complete the following CQN equivalence. Right? So you're going to be able to identify the form of this. Right? This is of course not a negation, it's a positive form. What is it? Existential quantifier tells you it's a particular, right? Not universal, but a particular, and then no negation on the predicate, so it's particular inclusion. This is the I form. You should all be able to recognize that, right? What does it say? There exists an X such that X is both a surfer and a philosopher, an S and a P. There exists something which is both S and P, saying some of the S's are P, right? Particular inclusion, that's the right, particular inclusion, so it's inclusion, it's either A or I, it's from the word affirmo, because it's inclusion, and it's, if it's universal, it's the first letter, particular is the second letter, it's I, right, because it's particular inclusion. It's the existential, so that's an I, so what's I equivalent to? I, right, A goes with O, not A goes to O, not O goes to A, I goes with E, right, not I goes to not I goes to E, not E goes to I. So this is I, so that goes to not E. That's the equivalence. That's the CQN equivalence. So I have to just put down the E form, put down the E form and negate it. So the equivalent E form is, right, this is E, hook negation. That is the E form, right? Now, when a not E, so it's negation like that, I just plug in the subject and the predicate, SX, PX, right? Now, please, highly, highly, highly recommended, translate it back to make sure what your symbol, read your resulting symbols back to make sure that what it says is logically equivalent to the original. So this says, there exists an X such that X is both S and P. Or some S's are P. This says, not all S's are not P. Right? Literally, it is not the case that there exists an X such that if X is an S, then X is a P. Or not all S's are not P. Is that the same? Yes, it is. Not all S's are not P. That's the same as some S's are P. Those say the same thing. Okay? So completing it, that's all you need for the final answer is this, right? Okay, are the following in quantifier form? This is question 7. Are the following quantifier form? Please read the whole question. It says, if not, say why not. You lose points if you don't say why not if it asks you to. Right? This is not in quantifier form because the two conditions for a formula to be in quantifier form are 1, the formula must begin with a quantifier, 2, the scope of the initial quantifier must extend all the way to the end of the formula. Right? That's the whole lesson of Unit 14. This begins with a negation and therefore it does not begin with a quantifier, so that's why 1, I, 7 part 1 is not in quantifier form. It begins with a negation. Right? It doesn't begin with a quantifier. That's the reason why. So that it breaks the first rule of being in quantifier form. Part 2, is this in quantifier form? No, it is not. Why not? It does begin with a quantifier, so it does satisfy the first of the two conditions for being in quantifier form. It does begin with a quantifier, but it fails the second condition of being in quantifier form in that the scope of this initial quantifier does not extend to the end of the formula. How do we determine the scope of a quantifier? We use our hands and we say, I'm going to move to the right, and as soon as I have a complete formula, that is what my quantifier governs. Right? That's the scope of my quantifier. Right? Fx, for our purposes here, that's a complete formula. That's what's bound by the quantifier. Remember, a propositional function annexed to a quantifier makes a simple quantified statement. So that's a sentence in itself with that. Fx, so it's just fx that is bound by the existential quantifier. So you must be able to recognize the form of this as, what is this? It is not a quantifier statement. It is rather a conditional, right? It's formed, right? That's its major operator, right? So if you were needing to determine the truth value of this, this is true according to, right? The truth or falsity of this is determined according to the truth table for the hook, because this is a hook. Right? This is a conditional. It's true just in case. It's true just insofar as it's not the case that this is true, and that's false. As long as you don't have T hook F, then this conditional is true, right? Because that's what the truth table of the hook tells you. So recognize that as a conditional, not a quantified statement. Again, the form of a statement is either a quantifier statement or a conjunction or a conditional or a negation, right? One or the other. Absolutely crucial lesson. You need to know it to be able to do proofs, right? Because you've got to be able to say of your premises and conclusion in proof whether they are in quantifier form or not, in order to know what to do with them. If they're in quantifier form, premises you can instantiate from UI or EI. If the conclusion is in quantifier form, you can use a generalization rule to get to it, UG or EG. But if it's in truth functional form, you have to use the truth functional rules. You have to use the modus ponens, the modus tollens, simplification, right? Whatever. Disjunctive syllogism, whatever it is. Right, so if this was a premise in a proof, you'd be thinking, oh, I'm looking to use modus ponens or modus tollens on this, right? If I can get this formula, there exists an x such that fx, I can do modus ponens, if I can get that out somewhere. Or if I can get the negation of the consequent. That's how you have to think of this, as being a conditional and thus having an antecedent and a consequent. If I get not for all x, gx, then I can do a modus tollens and get not there exists an x, fx. Right? Practice the question 4 of Unit 15, the non-pure, the mixed proofs, where you've got formulas like this as premise and conclusion to get practice in doing that kind of thing. All right, that's question 7. Neither are in quantifier form. This one because it doesn't begin with a quantifier. This one because the scope of the initial quantifier doesn't extend to the end of the formula. Question 8, state the following rules symbolically. Know the rules, know which ones are the flag rules and which are not flag rules. This, in the practice exam here, asks you for universal generalization. That's a flag rule. You just write, that's the hardest of the hard rule, right? So you have to, in giving the symbolic representation, you write flag A. That's the main line. If you learn it as per the book, you can put phi A here, but I will accept just FA for all x, F, X, U, G, right? You have to include the flag step, the flagging step, setting up the flagging subproof as part of the symbolic expression of the rule, right? The propositional function at the bottom of the subproof, the propositional function as true of the individual A, the flagged individual A. And if you can derive that formula within the subproof, you're entitled to infer that what is true of A is true of everything. That's what universal generalization is, as I taught in the lectures for this, for all of these rules, right? The name of the rule sort of tells you the basic form of what it is. What is universal generalization? It is generalizing, so it's going from an instance to a quantified formula, to which quantifier I'm adding. Existential generalization is adding the existential quantifier, going from it's true of some individual to there exists an x such that that thing is true of x, that propositional function is true of x. It's existential generalization, which is obviously true in all cases. It's no problems, because if something is true of some individual, you're entitled to infer in all cases that it's true of something. Right? This is universal generalization. It's true of some individual, therefore it's true of all individuals. That's what universal generalization is, just thinking the name, just deriving from the name of the rule what it is that it allows you to do. And if you consider that, it's true of some individuals, so it's true of all individuals. clearly that's going to require restrictions, and that's why this is one of the hard rules, right? Which means a rule which requires flagging. It's the harder of the hard rules in that you have to set up a whole flagging subproof before you derive the formulas you need to get to the particular the particular singular statement from which you do the universal generalization. All right, question 9. Two of the three rules governing flag letters are broken in the introduction of A as a flag name in step 4 below. You should have it in front of you, but there it is. If you want to pause. Yep, there's only really 2 rules you need to know for this exam. The third one doesn't come until the unit 17, 18 stuff. But at step 4, GA there, okay, that flag letter is not new to the proof. It already appears in step 3, right? So the first rule, it's broken 2 rules. The first rule that's broken is, talking about step 4 here, the flag letter is not new to the proof, and the second rule is that flag letter also appears in the conclusion. The rule is the flag letter cannot appear, the rule is a flag letter may not appear in the premises or the conclusion of the proof. Second rule. First rule is flag letter must be new to the proof. All right, so that's that. We'll come back for part 3 and start on symbolizations.